All right, let's do some fun stuff. Let's actually break out the sharp sensor. So the core of this project is a air quality sensor, and this air quality sensor looks at the change in a infrared signal fired across a gap as a result of particles in the air. And so this could be really any particle within the size range, but these are kind of micron to submicron particles that it'll detect. So these could be things like dust, these could be things like smoke, these could be things like droplets that were emitted from somebody's mouth who has coronavirus. Or it could be, any kind of, anything that causes air impurities. It's usually, these types of indicators are an indicator of how well filtered the air in a room is, or if there's something that's producing a lot of poor quality air, how much poor quality air it's producing. In environmental monitoring, these are sometimes used outdoors. So cities that have really bad smog, really bad pollution, these are often a useful indicator for exactly how bad it is. They give you a way to quantifiably measure the amount of smoke. And that's the basis for this project. And again, this project is really all about, I say again, I don't think I've said it in this video series, it's about taking a signal from this sensor and displaying it in a way, using op amps to produce circuits that produce a signal that a human can see immediately and say, yeah, this is really good, yeah, this is really bad, right? A nice little visual indicator. So it translates data into something human. And that's what op amps are really great for. Op amps are great for taking real signals from the real world and putting them in a format machines can read, and also taking signals that machines can output and putting them in a format that the world can read. So sometimes it's voltage to current, sometimes it's current to voltage, sometimes it's voltage to voltage. So we're doing all these sorts of translations and adaptations of signals, and that's core op amp behavior stuff. I said I was going to break out the sensor, and then I just kept yammering. So let's just plop the sensor down. So components, sharp air quality sensor. Now again, I created these components, so if there's something wrong, no warranties is stated or implied, blah, 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 blah. Right? John Lund is not responsible for any damage that's caused by... So I'm going to very quickly, just so we can actually see it on the physical board. Look at that thing. Oh my God. That's just incredible. Look at the size of that thing. So that's the sharp air quality sensor, and that is a whopper. And the one thing to note about this is, there's a hole in the middle of it. So if I switch to 3D view, there's a hole in the middle of it, and this hole is, where air is, it allows air to pass through. So ultimately, if I remember, we might want to poke a hole in this board so we can actually have, if we place this on the board, we want to poke a hole in it. You have options for this sensor. This sensor's a big, bulky thing. You can put it sideways. You can put it, ultimately we're going to have to kind of glue it or sticky tape it to the board or something. It doesn't really have mounting screws that are great for attaching it to the PCB. Actually, it might. I shouldn't say that. But, I mean, we have quite a few options for how to mount this thing, what to do with it. I'm going to just put it on the board. I'm going to actually just have a space on the board for it. We got room. But it's definitely the elephant in the room here. And the side of the sharp sensor, if we go to the course web page, oops, if we go to the data sheet for this thing, oh, do I not have it? No, I do. So here's the data sheet for this sharp sensor. And you see it, right? This is the mechanical structure of the thing. A couple of things for requirements for this, right? So one of the things is the power supply requirement for this should be 5-volt supply, and the supply should go through a 150 ohm resistor into a 220 microfarad capacitor before powering this thing. This is a weird requirement. So basically what they're telling us to do is they're telling us to RC filter this power, and I mean really RC filter this power. Why might that be? Why have this bizarre, it only consumes 20 milliamps, and they want us to filter this huge RC filter on this thing. Well, the reason for that is the way this thing detects particles in the air. What it's doing is it's emitting an infrared light, and it is looking at how much that received light wiggles. So there's a diode receiver, an infrared emitter, and on the receiving end, any little jitter that it sees in the signal, it assumes is due to, you know, little dust particles or little particles of COVID coming in between the sensor and the receiver, coming in between the emitter and the receiver. And it is amplifying that derivative. So it's taking, so any little jitter in the signal, it's taking the derivative and it's amplifying it, and then it's rectifying it, and that's the signal coming out of this thing. And the problem with that is, that means that you are dependent on your excitation for your emitter being very pure. If your emitter infrared signal is all jittery like your power supply, well, then it's going to perceive that as dust, and it can't have that. So the reason this has this really big 150 ohm resistor and then a 220 microfarad capacitor, which is huge, that's a big capacitor, is so that it gets a nice, pure, perfect supply signal, so that that infrared light that it shines is wiggle free, so that any wiggle in the signal that's received, it assumes is actually due to air quality issues. All right. So we're going to have to do that. We're going to have to create this RC filter here. The other thing is, this thing takes a pulse. So it's not just running constantly. It has an input that when that input sees a pulse, it then outputs this. So basically, when it gets a trigger pulse, it does this derivative and rectification and averaging of it, and then exactly 0.28 milliseconds, that signal hits its peak, which corresponds to the actual measured value. And this sensor is meant to be used in digital systems, where in digital systems, a digital system could have very accurate timing. It could send out a pulse, then it could go back and, you know, exactly 0.28, exactly 280 microseconds after it sent the pulse, it could read an analog to digital converter. It could capture that data as the actual air quality. We're trying to do an entirely analog circuit though, and so we're going to have to find some workarounds around this. So in this video, the goal of this video is going to be to one, get the sharp sensor down, get it powered with this weird RC filter, and then two, create op-amp circuits that will, one, generate a series of pulses that can be used to excite this thing, and then also have a circuit that detects the peak. So it takes this peak that comes out and does peak detection on it, and then it averages those peaks, or it smooths out those peaks, low-pass filters the peaks, and then isolates that signal through a gain of 1 gain stage. So, all right, so there's your lab. You have a lab that basically kind of goes over these topics, so I'm not going to spend too much time. We're basically just going to build it. But we're going to start by, and just also to note, these little holes next to this sharp sensor, there's a little jumper connector and loose wires, and so basically you're going to have to manually solder in wires to this thing. So you're going to have to, you know, connect the specific connector cable, but then take the stripped wires, feed them through these holes, and solder these manually. So, but the nice thing about being through holes is you have a little more flexibility in the sense that all that matters for the sensor is what's here. So, you know, this sensor, you don't have to use this footprint for the sensor as shown here, as long as you get the hole, as long as you get those ribbons in the hole. So, all right, so let's go back, and let's just, I'm just going to build the, it's called an Astable multivibrator. It's a way that you can, with a single amplifier, make a square wave, make a periodic square wave. And so we're going to use that periodic square wave to excite this sharp sensor. Let's piece it together. First thing we're going to do is put down our LM358. So we're going to place this op-amp here, and you notice, zooming in, when I place this, it says U question mark A, and then right after I did it, it shows me this U question mark B. And watch, I'm going to drop down this U question mark B, and then now it goes back to U question mark A. What's happening here? What's happening is we have two physical op-amps, we have two op-amps on one physical chip. And this Altium software knows that. The Altium software knows that there's two parts for every one chip. And so part one is this op-amp A, part two is op-amp B. And so we can place 2 op amps in our design, and Altium knows this is actually only one physical chip. So we might as well drop these 2 at a time, right? If we just drop one and then cancel selection and then go select the op amp again and just drop one, we're only going to be using half the op amps on the chips that we have. So every time we place these op amps, we might as well drop 2, the A part and the B part, and then use those up and then go from there. So, okay, so I dropped those 2 op amps, again, corresponding to one physical chip. Now I'm just going to build the circuit for the Astable multivibrator here. So, and to do it, Res 3, 0603, place it. So I gotta go back to my design. So with powering these op amps, you don't have to power them both because now we also want to be careful. We definitely want to power these with this 5V0. You don't want to accidentally power these with like the VBAT or VUSB. But these are the same pins. Pin 4, pin 8, pin 4, pin 8. It's shown twice on the schematic, but it's the same physical pin. And you have to be careful. You don't ever want to connect 2 different signals to these because these are the same physical pin. It's going to throw a fit if you try to connect 2 different physical signals to this. But something to keep in mind. So again, control click to move the part along with the wiring. I'm stuck in something. I don't know what I did. Oh no. I got into some weird mode. What is going on? All right. Oh, I know what happened. It lost its connection to the license server. All right. Oh, look at that. Oh, that's weird. That was strange. Oh, you You saw it happen live. What happens when you lose your license? It doesn't let you save. It doesn't let you even. Everything was grayed out. That was bizarre. I've never had that happen. That was just weird. Okay, now we need a capacitor here for this, and typically this resistor, when I did it, I made this 1 mega ohm. And in that case, a 10 microfarad capacitor is just fine for this, or something within that range. So for this, we're probably even okay with just doing a ceramic. So cap semi 0603. Let's just specify this is 10 microfarads. And it might be, you might want something smaller than that, or we might want to change the frequency, and you'll see this in the lab. You can change the frequency of this based on this value and everything. But so this is an astable multivibrator. So the way this thing works, it's fairly straightforward if we just want to quickly talk about it. Assume this capacitor is discharged. Assuming this capacitor is discharged, then what we have here is we have a little voltage divider. And this voltage divider is producing, the voltage here is about half of 5 volts. So it's about 2.5 volts. But there's also, there's the output of the op amp through this 20 kilo ohm resistor is able to pull this voltage a little bit higher, a little bit low. So it can pull it a little higher than 2.5 or a little lower than 2.5. And I think it ends up being something like 2 volts to 3 volts. I can kind of shift it about half a volt around. I mean, you can do the divider if you want to actually see exactly what it is. But when the capacitor is discharged, then this voltage here is definitely going to be lower than over here. So the op amp is going to amplify this, and it's going to produce a very high it's going to rail out here. So when this is discharged, this is 0. This is anything other than 0. It rails. So this rails high. When this rails high, this resistor pulls this voltage up. So it pulls it a little above 2.5. So it's going to be something like 3 volts or so. And then over time, though, that high rail is going to charge this capacitor up. And it's going to charge this capacitor until this voltage here gets above that 3 volts that's here. And as soon as that happens, then the output rails in the other direction. But because the output of the op amp was tied to this bridge, as soon as this output rails low, it actually pulls this bridge down from like 3 volts back down to like 2 volts. So now it's not simply a matter of this op amp. This op amp doesn't just have to drop this voltage now back down below 3. Now it has to take it all the way down to 2. Now it has to pull it all the way down to 2 volts before it reaches that threshold, and then it bounces back up. So what we're doing is we're adding an element of positive feedback that causes this voltage bridge to shift its voltage as the op amp rails in either direction. And that means that it takes time for the op amp, when its polarity switches, it takes time to charge and discharge that capacitor to reach that new threshold value, to reach that new voltage reference value. And the time it takes, that RC time constant, determines how quickly this astable multivibrator switches back and forth. And this is a really cool, it's really simple, really cool circuit that you can use anytime you need a pulse train. There's a formal version of this called a 555 timer. People might be familiar with it, where basically it's effectively this circuit, but there's all sorts of other neat things you can do with it. But this is, at its core, it's doing this. At its core, it's sort of using RC charge and discharge with a circuit that shifts the voltage set points required to reach equilibrium across the input terminals, and that allows it to create these sort of astable operation. So, but for us, this is generating this pulse train. And so this pulse train has to be connected to the T LED. This is the trigger LED signal. So this pulse train has to be connected to the trigger LED. Now the ground LED, that's just going to be ground. That's just going to be our system ground. And the V LED, that's going to be our 5-volt signal, but it's got to go through that filter. So maybe I should move this thing over a little bit, give ourselves some space, and then let's pop a we got to do a 150 ohm resistor, right? So let's just pull one of these guys. I think the data sheet said it's supposed to be 150. And then a capacitor, we need to use a very special capacitor that I bought. These are not cheap. This 220 microfarad tandem capacitor. These do have a polarity, so you always want to make sure you have the polarity in the right direction. And then this is grounded. Oops. This is grounded. And this is 5 volts here. And we're going to wire this here. And we're going to, we might as well just steal the ground signal from up here. Okay. So hopefully you can see what went on here, right? So we have 5 volts going through this RC filter. Again, that's to produce that really smooth voltage supply for the LED. LED is grounded, and then we have this Astable multivibrator producing the triggers that are going to actually cause this thing to do a sample. And then, okay, yeah, let's just go ahead and just do the output now. So for the output comes in pulses. So the output comes in these little pulses that we showed that in the data sheet. So they come, there's these little pulses, right? And that's not a great shape for a signal. It's not very useful. So what we're going to do is we're going to add a peak detector to that. And a peak detector is very straightforward. A peak detector is basically just a diode. So if you have this signal feeding into a diode, and on the other side of that diode is like a capacitor, then as soon as this voltage, as the higher this voltage goes, the more it's going to charge that capacitor through the diode. And when the voltage drops back down, the voltage across the capacitor is not going to drop back down because there's a diode preventing current from flowing back to the input. So peak detector is as simple as a diode and a capacitor. And we don't want this thing to save the peak forever, though. We want it to, we want to pulse this thing periodically, get these peaks, but we want over time, we want the ability for that signal to drop back down. If the air quality gets good and the voltage drops, we need it to actually reflect that. We can't just simply keep a capacitor charged forever, and that would be the worst case air quality is forever the air quality that it's measuring. No, we want to have some time constant to let it sort of dissipate. So let's build it. So first of all, we're going to power this thing. We're going to do, and this is fairly straightforward. This is just powered by the ground signal. It's powered by ground. The V signal is powered by 5 volts. So we could do this 5 volt upside down, but kind of by convention, we like to keep these in the right orientation. So I know this looks a little silly, but that's kind of that's how people do it, trying to keep it polite. It looks like I lost my connectors here. So that signal now, this signal is that sort of, the signal is these series of lumps that are coming off this. So what are we going to do to that? So again, as I mentioned, we're going to run this through a diode. So let's look at components. I don't think I have one here. We'll just use a through-hole diode, though. So we'll just use, and I don't know what diode we're going to end up really wanting to use. Probably something more like this. We'll see. If it's going to be a through hole, we're kind of flexible. So let's just place this. So we have this diode, and then we want this diode, we want a capacitor here. And let's give ourselves some options with the capacitors. Let's place 2 capacitors. So let's place, let's use the same 2 capacitors we used here. So let's grab one of these. See, now you see what it did when I shift grabbed this? Whoa. It created this C5, so it called it C5, but C5 already exists, so that's going to be an issue, and I'll show you how to do that. So let's just get, we're going to put, again, if we put 2 capacitors in parallel, we don't have to populate them both. It just gives us options. So it gives us options later on for this. And I'm just going to manually do C question mark. And again, we could have gone in and we could have done like back annotate all duplicate component values, which is a function feature that'll do that. Okay, now that's it. This is our peak detector. We've built a peak detector, but again, we want to have some way for these capacitors to discharge. Now they will probably self-discharge a little bit, but we don't have control over that. So what we'll also do is we'll also put like a mega ohm resistor in parallel with those. So put a mega ohm resistor in parallel. It gives us something we can control. Okay, and then now this is a very weak signal. I mean, this signal, because of that mega ohm resistor, this signal has supply. It's got like a mega ohm supply resistance. So, so we definitely have to buffer this signal. So to do that, we'll just do just a standard buffer. I had lost my power supplies here. I don't like when it doesn't touch the edge. There we go. Okay. That's it. We buffered it. Okay. Let's see what this looks like. So we've actually done a lot. I don't usually like to do this much before I actually start trying to piece the parts together. But because both of these op amps were on the same chip, it kind of makes sense to just know where the components are. But I'm definitely going to come back to this circuit to see the physical structure of this. And I'm gonna kind of assemble this on the board as its own little thing. So we're going to do, first of all, let's save tools, and I clicked the wrong thing. Annotation. And notice some of these components are big, right? This is that 220 microfarad capacitor. That's really big. I mean, this is the op amp chip, so the capacitor is way bigger than that. So what I'm going to do now is I like to just kind of go back to the schematic and just start piecing things together as needed. So we have this 1 mega ohm feeding back. So let's get the op amp. And the 1 mega ohm was R6. So let's just take our op amp, make it the middle, find that R6. And we know that's got to be a feedback. So we're going to rotate it till those air wires aren't crossing. And that looks like a pretty good spot for it right there. What else do we know? We also know that we got R8, R7, and R9 make this T here. Why do I keep doing that? So let's get R7, R8, and R9. And let's get them taken care of. And again, these are all part of that same logical op-amp, so they should be on the same physical side of the chip here. This one's got to be powered by the supply, so this one's on the supply side. This one's on the ground side. Oh, no, wait. Yeah. Supply. That's going to work. I think that's going to work. Looks like we can also move this one up here. And sometimes when I kind of think it works, I'll kind of do a little bit of intermediate routing. We're going to probably regret that later, because I think this signal is the signal that comes from the outside world here. No, we'll deal with it when we deal with it. And, you know, nothing's set in stone. We can always rip this stuff up. So whenever I have wires routed under a chip, I really want to keep them away from those pins, because it is possible to have, to accidentally, if the solder mask is, that's probably something I should talk about. So all this green on this page, this is all solder mask, right? So there's sections, everything's covered with a mask that solder is afraid of. So solder phobic, right? Solder isn't going to go anywhere where this green is. But wherever you have pads that need to make a solder connection to a chip, you have to have an opening in that solder mask. And if we go back to this thing, you can see it if you go to the layer, if you scroll over and go to layer top solder. So see, this shows where the openings are in the solder mask. The solder mask layer is defined by, you define all the places where it's open. So if you click on this top solder layer, you can see this. You can see all these openings in the solder mask. And the problem is, if this is a little bit misaligned, if the fab, when it's making this layer, when it's printing these boards, if this layer is a little bit misaligned, it's possible if you run the metal too close to this other metal that it's going to expose just a little sliver of that metal in there. And then it's possible to get solder bridges. So I always like to keep, if I'm routing metal around these openings in the solder mask, I like to give them space. Unless I have to keep them tight, I'll give them a lot of space. So, and I probably am kind of going overkill with it, but you know, it's one of those things where if I don't have to keep it all nice and compact, why not, right? Why not give it some space, give it some breathing room here. Okay, what else do we got here? We got this net 7. net 6.1 and net 7.2. Are these in parallel with each other? Oh, R2. Oh, C7.2. Oh, we need that capacitor too. Ah, oh, C7, man. Let's get that capacitor in on the show here. What's your story? What is your story? Let's go back and look at the actual schematic here. C7 and that 1 mega ohm should connect to the negative terminal resistor, which is pin 2. So I'm going to go back to the drawing board as soon as this happens. There are better ways to do this, so I can just click these components and unroute them. Okay, so I know that these two need to be connected to that pin. So let's start by focusing on that. I know that net R7 needs to be there too, so maybe I want these to be on the outside. It needs to be on the inside. Nope. Go back. I'm not good at this too, I'll admit. There's some of you will probably find you're a lot better at this than me, and you're probably having an aneurysm trying to watch me. You're probably yelling at the screen saying, "Ah, there's a way to do it. I see it. I see it." Doesn't help. Doesn't help me. You know what? Sometimes you gotta just give it a shot. Actually, that looks pretty good. Yeah, I think that's going to be okay. All right, so let's route these up then. Okay, so this is gonna seem a little weird. I'm gonna snake this one through. Neat. Okay, so for now, we'll call that a victory. Now let's go to the other side. The other side of this is this circuit over here. So we have D1 feeding into the caps and the resistor. This is going to start to get weird because these are some big components. Should be this cap and this resistor and this cap. Oh, and that's right, that's coming from there. Just put it like that. I love it. And, you know, let's put this next to this sharp sensor for now. I don't really know how we want to do this, how we want to orient this entire thing. We may want to, though. You know, do something like this. Yeah, let's just commit to it. I'm just going to do it like this. We'll just put all this stuff in here. Now, I'm not going to worry too much about power right now. I'm not too concerned about power yet. About running power to this circuit is what I mean. But let's just get this lined up. Let's get this kind of connected up a little bit more. So this is that big old capacitor that it needs. There's that resistor that it needs. Power. Do I like this? Maybe like that. Is that too tight? Maybe. Maybe it's too tight. Perhaps. let's see what we can do here. Let's start. I'm just gonna commit. This is it. It's gonna be like this. That's how it's gonna be. Yep, that's how it's gonna be. I have spoken. So we'll just start wiring up what we can. See how it goes. I got a thing with clicking the wrong buttons today. So again, we'll get power and ground in this thing later. I'm not gonna worry too much about it now. I'm gonna connect it up as best I can, but beyond that, we're not too worried about making the power and ground connections. This R61, I knew I kind of isolated the R61 in here, so we might as well do that now. What I'm gonna do is I'm gonna click on this wire. I'm gonna have to place. I'm gonna have to punch through the board. So I can hit, while I'm doing the wire routing, I can hit the plus key, and that drops one of these through holes here, vias. And then, while this is too big, that's too big. While it's selected, I can do the hole size. I tend to like 13, and the entire diameter is 25. It leaves a nice 6 mil ring. Yeah, that's a better size here. And then we can route this signal back here. And you can see what that looks like in 3D. In 3D, that looks like a little hole here. And we'll talk later on about how to cover that up, about how to tent that. It's called tenting. And D1's gonna be easy. We can just route on the bottom. We're already on the bottom layer. We can route D1. Oh yeah, we gotta go around the connection we just made. Not a problem. And then I know there's a through-hole connection here for 5 volts, so I might as well just use that as a jumping off point for powering this op amp. So I don't want to do that. Switch to the top layer. Okay. The ground connection here, this one's fairly easy to do. Said I wasn't going to worry about the power and ground, and here I am doing it. That one I'll get later. Some places don't like side entry into pads. I've never had an issue with it, but it's just something to note. It's kind of forbidden by some. I mean, it's kind of considered bad practice in some cases. You know, I'm gonna move this diode. This diode doesn't have to be here, so I'm gonna. I mean, this actually fixes a lot of issues by just moving that diode up to the top. And that happens sometimes. Sometimes you'll see connections that after you do it that seem obvious only after you've done it. And then we can just run the ground straight across. Still have some powers that will have to be connected. That's okay. Another thing, let's just save all for now. Another thing is op-amp decoupling. A lot of times it's good to add a decoupling capacitor as an option for the op-amp. So why don't we just do that? We'll just add just grab a capacitor, like one of these. And then we're just gonna, oops. So we're going to give ourselves a capacitor just to smooth out the pitch. For stability, a lot of times, it's not going to be a case for us because it's kind of a low-speed circuit, but for stability, a lot of times with op-amps, it's just good to have a capacitor near the op-amp itself between the rails. So didn't like that. So I'm just going to put this here. the best way to do it. You'll find a better way than me. You'll find when you do it, you'll do better than me. Learn from my mistakes. I don't know what's going on here right now. All right. Let's see how it looks in 3D. Everything but the annotations. Okay. So we'll just get things a little tidied up here. So again, selecting things a lot of times is the hardest part of looking for this one's annotation. It was hiding. That maybe is a little ambiguous, but I think we'll get it. How are we looking now? Pretty good. Pretty good, except for this one over here. All right. So that is the sharp sensor portion of it. That's the sharp sensor driver, and the pulse generator, the signal generator, and the peak detector and buffer for that. And that only took one op amp. So all of that only took one op amp, kind of a mess of a circuit. So what we have left to do is to take this signal and run it through the actual sort of filter signal that we built. So we'll try to, I think what I'll try to do is maybe next time, try to fill that in here. Try to maybe put that circuit in here in the middle. And then we'll do the LED action over here somehow. We'll do some sort of kind of going as I go. We'll save that for next time. So thanks.